from our perspective in the lab, we're going to look at how we're going to use what we learned in the lecture for problem solving, for understanding where the true mean is when we take a sample and we have certain information about the population. Okay, so let's take a look at what we might know about a population. One thing we might know, for starters, is we know what the population mean is and the population standard deviation is. Do we need a confidence interval? No, we don't need it because we know what the mean is. What uses a confidence interval? We don't need it at all. Confidence interval is only for situations where we don't know what the mean is, and we want to inform ourselves about how accurate we might be with our prediction of what the population mean is. So if we know the mean and the standard deviation, we know the population. We don't know anything. We don't need to go any further than that. Okay, so one situation that we might have is that we take a sample, right, of size n, and we know the mean from that sample, and we also know the standard deviation, sigma, for the entire population. That going to happen very much? Not really, but it's a learning tool for us that we know sigma, because sigma is what we need to apply the central limit theorem, to know what the true distribution of all the samples, if we took them over and over again, would be, what that distribution would really look like of all the possible samples that we would take from that population. Well, I'm gonna break that down to two possible situations. I could take a sample mean and know the standard deviation, but I could have a large sample size or a small sample size. Does it matter whether I have a large sample size or a small sample size? Well, it does, because when I calculate my standard error, the size of the standard error is based on sigma over the square root of n. So the smaller the sample size is, remember the sample's on the bottom of the fraction, the smaller the sample size is, the bigger my standard error is going to be. The bigger the sample size, the bigger the number on the bottom is, the smaller my standard error is going to be, my sigma over the square root of n. But in both cases, since I know sigma, I can apply the central limit theorem, with a lot of confidence, because I know exactly how this population is distributed, right? So large sample size, small sample size, that's going to correct for itself because we know sigma. Okay, what's the next possibility? Well, the next possibility is the boat that we're all going to be in together. Anybody ever see that movie, what was it, Lifeboat? An old Hitchcock picture where, these people are stranded in a lifeboat and one of them's secretly a Nazi and the other guys are, and there's all this intrigue on and they're running out of food and water and so on. So we're kind of in that lifeboat. When we don't know the population standard deviation, we're in that lifeboat with them. We have much more uncertainty because we're completely reliant on that sample that we took. So we can have a situation, which is what we real life are going to come across most, where we know that we know our sample mean and we know our sample standard deviation. Well, we know because we're experienced with sampling things now that our sample mean probably approximates the population mean. Our sample standard deviation, since we took a good random sample of this population, our sample standard deviation approximates the variability in the population itself. It also represents, standard deviation also approximates the standard deviation sigma of the population. Now, but the central limit theorem really helped us out because since we knew sigma, the only place where we have a lot of uncertainty is in the sample mean, right? But now we have two levels of uncertainty. So we could have a situation where we have a large sample, right, big N, and we know the sample mean and sample standard deviation, but not the population standard deviation. Or we could have a small sample where we know the population standard deviation, where we know the sample mean and the population standard deviation. Big sample or small sample, same knowledge about the distribution. When we have a big sample, even though we don't know the population standard deviation, we have a lot of confidence that we have enough people in our sample that we have a pretty good guess at it. When we have a small sample, we get into an area where we have a lot of uncertainty about what the real variability of the sample is, right? So in the first three situations here, when we know the population standard deviation, whether it's a big sample or a small sample, we're going to apply the central limit theorem. And we're going to cheat a little bit, and we're going to apply the central limit theorem just the way it is when we have a large sample size, even if we don't know the population standard deviation. We just know the sample standard deviation, but the sample size is big enough for us. When we get to a small sample size, we're in a real shaky area here. We have to make accommodations for the fact that there's more uncertainty here. Now, when I say that we're going to cheat a little bit with large sample sizes, when you use software like SPSS, SPSS never cheats. SPSS always assumes you make an accommodation for the sample size, whether the sample size is 10, 100, 5,000, doesn't make any assumptions. And the way that it does that is instead of using the z-score, it uses, as we're going to be doing in the future, it uses something called a t-score. The t-score is an accommodation for our level of uncertainty. Okay, it's based on the sample size. In fact, there's just like there is a distribution for the central limit theorem, that normal distribution that we use, that tells us that 95% of the sample results are going to be between 1.98 standard deviations below the mean and 1.98 standard deviations above the mean. Just like that, for a infinite sample size, when we know the population standard deviation we use that 1.98 to give us our 95% confidence interval, that range of standard deviation of z-scores. When we don't know the population standard deviation, well, we have a different distribution of possibilities for every sample size. There's one t-distribution for a sample size of 100, one for a sample size of 50, one for a sample size of 49, and so on and so forth. As you can imagine now, and what happens is that t-distribution for each one of those sample sizes is flatter and wider because we have more uncertainty. The spread is wider. We can't be as certain that we're going to get 95% of our results within a certain area, so it gets spread out. The smaller the sample size, the more spread out it is. The larger the sample size, the narrower it is until you get a sample size that's infinite, and then it's the same exact distribution as the z distribution, our normal distribution. So our t-score is going to accommodate for that extra uncertainty. So we're going to start off with some examples where we just apply the z-score. We don't have to worry about it because I'm going to make up some stuff where it's kind of an artificial situation, but where we know the population standard deviations. I just noted down here, all these different possibilities. Then I also noted down there that that when we're dealing with the z-score, when we know the population standard deviation, or it's a very large sample, and we're willing to guess at it, for a 95% confidence interval, how do we calculate a confidence interval? The mean of the sample plus or minus the z-score for the level of confidence that we want, 90, 95, 99. The z-score for that number of standard deviations for that level of confidence times the standard error, which is calculated from sigma over the square root of n. Okay, so for 95% confidence interval, we use 1.98. For 90% confidence, we use 1.64. And for a 99% confidence interval, we use 2.58. Which is a wider range? 99% confidence interval or a 90% confidence interval? Right, because it's got to be wider because you make it wide. First of all, it's wider mathematically because you use a bigger z number for the number you're adding and subtracting from the mean. So mathematically, it has to come out wider because for a 90% confidence interval, you'd only use 1.68. So it would be a narrower range. And for 95%, which is in between, it would be somewhere in between those two, right? 1.98. Okay, now intuitively, that makes sense because If you want to be more confident that you captured a real mean from your sample mean, you make a wider interval. Now you're more confident that the true population mean is between the two. Yes? I'm sorry, 1.96. Did I write 1.98? You're absolutely right. It's 1.96. Good catch. Probably because I was looking at 2.58 at the same time. Okay, so now when we look at our t-score, right, one of the things you'll notice is that the t accommodates for an extra level of uncertainty. So the t is, every situation, the t is always more than what the z would have been. Okay, so a 95% confidence interval, the lowest that t can be is 1.98. That's for an infinite sample size. And for 90%, it's at 1.64. And for 99, 2.58. But in real life, because depending on the sample size, it's going to be bigger than that. Now, we're not going to have a table like a z table for every sample size for t. And we don't need one because with t, we're really only interested in three values. What it is for a 95% confidence interval, what it is for a 99, what it is for a 95% confidence interval. So if you look on Blackboard and in your open source textbook or in Agresti, if you look at that, if you look at those, you're going to find that the t-table looks something like this. Here's what the z-table looks like. The z-table gives you specific areas under the curve, under a single curve, a single distribution that you need to predict what's the probability that you get an outcome, bigger or smaller than something. The z-table just summarizes that, right? And if I go all the way down to the bottom, down to infinity, you'll notice that, well, what does it do this for? It does it for a 95% confidence interval. Right tail probability is equal to 2.5%, 0.025. What does that mean? That means the right tail 2.5%, left tail 2.5%. So that's in between is 95%. So a right tail probability of 2.5%, since it's symmetrical, is the same thing as a 95% confidence interval. So the t-score for an infinite sample size is 1.96. It's the z-table, right? So since we're never going to do that, what we're doing instead is we're working with sample sizes, different sample sizes. And the sample size, rather than describe the sample size, most all t-tables show something called the degrees of freedom. Anybody know what the degrees of freedom is going to be equal to for a certain sample size? N-1, sample size -1. Okay, there we can talk about where that comes from and how we might look at it, but that's basically it. So for a sample size of 25, the t-score, the substitute for the z-score that we're going to use for a 95% confidence interval, that's this middle column or near middle column, is going to be for 24 degrees of freedom. It's going to be 2.064. Okay, for a sample size of 30, it's going to be 2.04. It's a little bit more than 1.98. And as the sample size gets bigger, it gets even closer and closer. A lot of statisticians, especially when they're initially examining their data, will say anything bigger than a sample size of 30, I'm going to say that that's a large sample. And for my initial analysis of my data, I'm just going to use 1.98. But anything smaller than 30, they're going to apply this t-test. What did I tell you SPSS does? SPSS is the most unforgiving statistician in the world, and it's got nothing to do but calculate this stuff. It always uses a t-test. If the sample size is 5,076, it's going to calculate a t-score, which might be 1.960034, right? It's going to find it ridiculously accurately, right? Because it has that capacity. It's not any harder for it to do it than for any sample size rather than all. So it's never going to give you a z-score. It's always going to give you a t-score. Okay, so let's apply this now. And in the beginning, we're going to apply just a z-score, right? And then we're going to examine the problem. We're going to make our decision about what we know and what we don't know. Okay, so there's two documents here that we might want to work with. One is something that's, let me find the name of it. Let's get rid of this thing. Don't need that. A confidence interval practice excel.doc. It's actually a Word document. but I have Excel in there because it's easy. You know, if you use Excel or a calculator, it's going to help you out a bit. So I'm going to open up Excel because that's my calculator here. You guys online can still hear me and see me, and you've gotten some of this, I hope. Hello, hello. Okay, good, thanks. Okay, let's see, view, zoom. Let's go to 200%, so we got nice big boxes. Okay, I'm gonna move this over here, I'm gonna move this over here, so I can see. Okay, sample size of 100 has a mean of 160. Assuming that the population is normally distributed with a standard deviation of sigma equals 30. What do we know here? We know our sample mean, we know our population standard deviation, or we're going to apply Z or T. We're going to apply Z, right? Because we know the population standard deviation. Compute a 95% confidence interval for the mean of the population mu. Okay, so it's a confidence interval. Okay, we got X bar, we got sigma. Okay, and let me see what I got here. Okay, so X bar is 160. Okay, what's N? N is 100. Okay, so let's calculate my standard error. What's my standard error equal to? It's equal to sigma. Excuse me, I didn't put that in there. Sigma was 30. Okay, so my standard error is equal to sigma 30 divided by the square root of 100. Basically just dividing it by 10. So standard error is 3. Okay, so now I know my standard error, and what is my formula for my 95% confidence interval? It's X bar plus or minus, right, this range. The Z-score for whatever our confidence is. Sometimes you'll see people write it, and then in small numbers down at the bottom, they'll put 0.05 for 95 or something like 0.01 or something like that. Or they might actually put in there that's what kind of confidence interval it is. Plus or minus, in our case, 95%, 1.98, right, times the standard error. Okay, so let's work that out. First number is going to be equal to 160, right, minus 1.96. Boy, I'm really seeing your moments here. Times the standard error, which is equal to 3. I calculated that already, so I'll just click into that box. Okay, and what is that? It's 154.12. Okay, and for our upper limit, it's going to be the X bar, which is 160, plus 1.96 times the standard error. Okay, which is 165.88. We're 95% confident. Oops, let me get in there and correct that there. We're 95% confident that our true mean lies between 154.12 and 165.88. Why am I so confident? I'm so confident because I know the population standard deviation. I know if the population is distributed this way, that this will work out for me. It's really going to be 95%. My level of uncertainty about the mean is going to be that it's going to be within this range. That's so much better than just knowing the mean. In other words, if I just took the mean and stopped there, I'd find the mean was 160, but I would have no idea what my level of certainty is. I wouldn't know if there's a good chance it could be 80, right? Since I only took one sample, I just don't know anything about it. But since I know the population standard deviation, it informs me about how the samples this size behave. Samples of size 100 behave. Okay, so look at the second part. If instead the population mean were known to be on what would be the probability of a single observation selected at random. This is nasty. I'm not going to skip that for now. I'm going to skip both parts of those. I'll come back to those later on. Okay, let's take a look at this next problem. After observing 36 randomly selected caseworkers, the supervisor noticed that the average number of cases carried by each worker in a week was 50. From previous long-term observations, it is known that the standard deviation for the entire department is 9 cases per week. Calculate a 95% confidence interval for the mean number of cases per worker per week for the entire department. Okay, so he sampled 36 workers and measured the number of cases that they covered. The average was 50. So in this case, our X bar is what? 50, right? That's how many cases each one of them did. And our N sample size is 36. They surveyed 36 workers. And our sigma is what? I lost it here. Sorry. 9 cases? 9. Okay, sigma is equal to 9. So we're asked for a 90% confidence interval. Okay, so the first thing I got to do is I got to calculate standard error. Oops. Okay, and our standard error is equal to, I'm going to put it over here this time, is equal to sigma divided by the square root of the sample size. Divided by 6, 1.5. Okay, so let's take a look at our 95% confidence interval. It's going to be equal to X bar plus or minus the z-score that I'm going to apply, and the z-score is going to depend on my level of confidence, times the standard error. Okay, now, only thing is here, we're asked several different confidence intervals. So I'm going to apply it first to a confidence interval of 95%. So what's that's going to be? That's got the lower range is going to be, the lower limit is going to be equal to 50 minus z-score, which is going to be 1.96, times the standard error, which is 1.5. And our upper limit is going to be, for a 95% confidence interval, is going to be X bar, which is 50, plus 1.96 times the standard error. So our 95% confidence interval is, and I'll put that over here, confidence interval 95%, is 46 to 53, basically. Okay, now let's calculate our 90% confidence interval. Now, you guys tell me, equals, the mean is equal to 50, right? Minus what? Opinions? What am I going to do now? Minus, this is for our 90% confidence interval, part B. 1 point, what am I putting there? 1.64 times the standard error, right? Only difference here was what our that affected our confidence interval was the width of the interval that we wanted, the level of confidence that we wanted. Now let's think about this. Since our confidence level, we're willing to have our confidence level be lower, our confidence interval is going to be smaller. So 1.96 times the same number is going to be a smaller number than 1.96, 1.64 rather. It's going to be a smaller number than 1.96. Okay, so that's going to be equal to 47.54, and the upper range is going to be 50 plus 1.64 times the standard error, which is 1.5, 52.46. So our range now is 47.5 to 52.5 rather than 47 to 53. Okay, how about 99% confidence interval? Is it going to be wider or narrower? It's going to be wider, right? Okay, so let's calculate it. Equals the mean minus, what am I going to use now for Z? 2.58. Where'd that 2.58 come from? Let's examine that right now. That 2.58 came from our Z table. And if I look up 2.58 in my Z table, this is just the right side, the minus 2.58. 2.50, 1, 2, 3, 4, 5, 6, 7, 8. It's about 0.005, about half of 1%, right? So that means that this area to the left of negative 2.58 is half of a percent. And to the right of plus 2.58, since it's symmetrical, would be half a percent. So what percentage of the outcomes are between the two? 99% of them hence the 99% confidence interval. That's where the number 2.58 came from. Yes? Oh, okay, thanks. Wouldn't the standard error question number 1 be 3, not 30? Yes, it's 3. What did I do 30? Let me go. I'm going to go back and look at it when I close this table. Okay, so if I look here for a 90% confidence interval, 1.64, 90% confidence interval would suggest 5% on the high end, 5% on the low end, 90% in between. So I would think negative 1.96, 0, 1, 2, 3, 4, 5, again is about 5%. 5% low end, 5%, 90% of the outcomes are in between the two. And 1.96 rather, would represent a quarter, 2.5% on the low end, 2.5% on the high end, and 95% of the outcomes in between. That's where those three numbers came from. If I asked you to calculate a 93.5% confidence interval, you could do it. You just have to look up what z-score to use. Nobody ever does it, but you could do it if you wanted to. Okay? So let's go back to our problem here. Let's see. Okay, so this is going to be 2.58 times, and I'm going to get to the question online. 2.58 times our standard error, and our standard error here, in this case, was 1.5. Okay, and it's going to be equal to our mean plus 2.58, because it's a 99% confidence interval, times our standard error, which is going to be 53. So this is the widest of the whole bunch of them. It's wider than the 95% confidence interval. It's wider than the 90% confidence interval. It's the 99% confidence interval. And it's widest because it has to be wider to increase our level of confidence of capturing the real mean, the real true population mean in there. Let me go back to the problem before. I think I did use, hang on a second here, B7 and B7. Yeah, Annie, I'm going to do it again here. I'm going to say, okay, in this problem, the mean is equal to 160, right, times 1.96 times the standard error. And I used 3, not 30 for the standard. See, I calculated the standard error, right? Oops, what did I just do? Up, plus, minus, rather, put it not, okay, 1.52. So I did use the 3 there. We calculated the 3 to begin with, so that I didn't have to do it within that formula. See, this cell here is B4, that's sigma 30 over the square root of the sample size, which was 100. Okay, good. All right, so we have some tools to work with this now. So now let's go on to the next one. See what that one looks like. Suppose we would like to estimate the amount of money, mu, spent on books. See, we're always after mu. We don't care. X bar is what is our tool, right? X bar is what we calculate, but we really want to know is mu, right? That's what we're really after, the true population mean. True population mean of how much cholesterol Americans eat versus Frenchmen, what the mu is for Frenchmen versus what the mu cholesterol level of Americans are. We want to know that, but we can't afford practically to actually calculate or get the data that we need to actually know what mu is. So we need a substitute. We need to calculate X bar and understand how accurately we know, how accurately it estimates the true population mean. Suppose we would like to estimate the mean amount of money, mu, spent on books by Hunter students in the semester. We have the following data from 100 randomly selected Hunter students. This is a little bit of an underestimate, right? The mean amount spent was X bar is $249. That could be one textbook nowadays, right? So that's a little bit out of date. The standard deviation is $30. Not much variability in there. Now that's the standard deviation of what? The sample, right? So smaller. This is an S, not a sigma. So we don't know the population standard deviation, do we? Assume that the $30 is, oh, hang on a second, I just changed something here. Let me see what the next one looks like. Okay, well, I'm going to do this one 2 ways. Assume that $30 is a good approximation of the standard deviation in the amount spent on books across all students. And in fact, I might have done that anyway.
Are you saying that you're saying that assume that S equals sigma?
Yes.
So then you'd use z-score?
I'm using the z-score. Now, why am I using the z-score in this particular problem? What did I tell you about sample sizes? I mentioned on sample size, you get a big sample size, like 100. A lot of statisticians, rather than going to the t-score when they do their initial evaluations of the data, they'll just use z because the sample size is so big. Let me look up the difference between the z-score for a 95% confidence interval and the z-score for a sample size of 100. The z-score is what for 95% confidence interval? 1.96. Let's see what it is for the t-score. For the t-score, sample size, sample size of 100 would be a degrees of freedom 99, but close enough. For 100, it would be 9.84. See how close it is for a sample size of 100? 1.96. So, why not just use 1.96 for an initial evaluation? Okay, so the trick here in this question is that since it's a large sample, I'm willing to forget the fact that it's a sample standard deviation and do the calculation as if I knew sigma for the population, that was a good enough estimate of sigma for me to call it for the population. Okay, so let's do it for this example. So my x bar is what? 249. I'm going to use numbers. I'm going to put dollar signs. My sample size is 100. Good. And my standard deviation, my sigma, right? I'll just put S, but we know I'm going to use it the same way. Is how much? 30? Okay. So now let's calculate our standard error. Our standard error is going to be equal to 30 over the square root of the sample size, 100. Yes, what did I do wrong there? Which is 3, right? 10 into 30, basically. Okay, so now let's do our 95% confidence interval. So our 95% confidence interval is going to be equal to 249, right? Minus 1.96. Right now, really that should be what number? If I wanted to be more accurate. 1.98, right? For the T, right, the T for 95. But we're not doing that. We're doing it this way, right? Because it's so close. Times the standard error. Okay, and my 95% confidence, upper limit 95% confidence interval is 249 plus 1.96 times my standard error, which is 3. Okay, so my 95% confidence interval is 243 to 254. Now, again, if I were to repeat this for 90%, what's the difference? It's going to be equal to x bar minus what for a 90% confidence interval? 1.64, right? Times 3. And it's going to be equal to my mean plus, again, 1.64 times my standard error. That's my 95% confidence interval. And finally, for my 99% confidence interval, it's going to be equal to 249 minus 1, what is it? 2.58 times 3 and equal to 249 plus 2.58 times my standard error. 90, my 99, 95, 90, and 99% confidence intervals. I'm going to change this problem right now. I'm going to say my sample size is 25. What do we say about a small sample size and we don't know the population standard deviation? I can't assume 1.96 anymore. I have to make a correction for the amount for the fact that I don't know the standard deviation of the population as adequately as I would like to use the z-score, right? That small sample size now gave me a second level of uncertainty, not just the mean, but now also the standard deviation. So I'm going to do the same problem now, except I'm going to use the t-score. What is the t-score that I would use for this example? What's the only thing that's changed here in this problem? Sample size. So we're going to go to a t-table. And the thing that's going to change for that t-score is still 95% confidence interval, but our degrees of freedom, our sample size is 25, our degrees of freedom is 24. What should I be using for my t-score? 2.064 instead of, I'm sorry?
Sorry, why not 25? Why are you using 25?
Because this list is not the n, it's the degrees of freedom. And the degrees of freedom are 1 minus.
Okay, yes.
Yeah, the
that's true.
sample size minus.
Sample size is 25.
Right. So I'm using 24 degrees of freedom because this table, if you look at the top, it's degrees, df, degrees of freedom.
Minus
Right, -1. Okay, that kind of makes sense because what kind of sample is a sample size of 1? You can't, a sample size of 1 is just one person. You can't have a confidence interval for a sample size of 1. If you take one person out of a population, right, and you say, oh, that person is 34 years old, right? How do you know what the variability in that population is? You don't, right? I mean, it could go from 0 to 110, or it could go from 32 to 30. You know nothing about the variability. So if you only have a sample size of 1, you can't calculate any kind of confidence interval. Once you have a sample size of 2, now you have some clue as to the level of variability. Not a very good clue, but you have a clue. So that's why these tables, they exclude the idea that you can have a sample size of 1, basically. Okay, so in our case, we use, and remember, this is just we know the sample size is 1. It's just this table is listed in degrees of freedom. So you don't have to worry about the idea of why. You just have to remember that don't go to 25, go to 24 because it's n minus 1. And what do I use here for 95% confidence interval for t? 2.064. Instead of using 1.96, for this sample size, I'm going to use 2.064. So I'm going to go back and do exactly the same problem now. Equals, okay, is going to be equal to the mean, right, minus, not the z-score now, the t-score, which is 2.064 times the standard error. And now on the other end, on the high end, it's going to be equal to 249 plus 2.064 times the standard error.
Wait, so,
Yes.
we have covered this already.
I'm sorry, say it again.
We may have covered this already, but in the T table, when it says right tail probability and then it says T
Yeah.
point
Okay.
what is that?
Okay. A 95% confidence interval. When you're looking at a 95% confidence interval, you're looking at, for repeated samples, you're looking at 95% of the possible outcomes for the mean from a given population. So the 95% is in the middle, right? So 1.98, 1.96 to 1.96 if we're a z-score, right? So how much is outside of that? 2.5% on one end, 2.5% on the other. So when they say 95% confidence interval, they just say right tail probability, but they really mean both tails are going to be 2.5%, 0.025. When they say a 99% confidence interval, both tails are going to be 0.5%.
But do you have to recalculate the standard error?
No. Oh yeah, I'm sorry. What am I saying? No. Yes. Yeah, I forgot all about that. Good point. Okay, instead of being oh no, I didn't have to recalculate. When I look back there, I said I don't remember it being 6. What happened when I changed the number 25? It automatically. Yeah. You shook me there for a second. I don't remember. You're right. I didn't remember doing it, but Excel did it for me, right? Because I had clicked into that space where the 25 is. Remember that used to be 3 because we divided 30 by 100. Okay, so let's do it for a what confidence interval we want? For a 90% confidence interval. Well, this is going to be interesting. Equals 2.49 minus What's the t-score I need now? I got to go back to that table again. Now, for a sample size of 25, which is 24 degrees of freedom, I need a 90% confidence interval, half on either side. So for 24, it's not going to be 1.64, it's going to be 1.711. Okay, is equal to 1.711 times the standard error, which is 238. Okay, equals, and the upper end is going to be 249 plus, what's the t-score again?
1.711.
1.7. Everybody see why it's 1.711 from that table? Times 6, and that's our upper range. Okay, so now let's do it for 99% confidence interval. It's going to be equal to 249 minus, and what is it going to be for a 99% confidence interval? Let's see, we got to go from down here. See, we skipped 98, 99. 24 is going to be, instead of 2.58, it's going to be 2.797. 2.797 times the standard error. And for 99% confidence, the upper limit is going to be 249 plus what was it again? Anybody remember? 2.797, I think. 797 times 6. Okay, now notice that all of the ranges, when we had to use the t-score, the confidence intervals are wider. For the 95% confidence interval, for the 99% confidence interval, for the 90, they were all wider because the t-score is always bigger than the z-score, right? Okay, so how are we doing on time? We're doing pretty good on time. Okay, I want to go over, there are more problems here, but this is how we're going to apply this. And one of the reasons we're so interested in this is, let's say that I told you that in France, we know that the average cholesterol is 180. France, they have a universal health care. Everybody in the country gets their cholesterol checked. It's recorded in the database. They don't have HIPAA in France, so you can go in there and you can get all the data. And we know that the population in France is, their cholesterol is 160. Okay, so now come to the United States. Well, not everybody gets it checked. We can't get the information. We randomly select 100 people in the United States, right? And we find that the average for those 100 people is 170. And we find that the standard deviation for those 100 people is, let's say, let me think for a second here, 10 is 50. Standard deviation is 50. What's the standard error for a sample size of 100? Standard deviation is 50. It's 50 divided by the square root of 110. It's 5, right? Okay, so now what's our confidence interval for those people? Say the United States, it turned out to be 175. It was the mean for those 100 people, randomly selected 100 people. What's the confidence interval for those true population mean cholesterol for Americans? 175 plus or minus 1.96 is a big sample, 1.96 times the standard error, right? I'm going to say roughly 2, right, times the standard error. Standard error is 5. 2 times 5 is 10. So my 95% confidence range for the true population standard deviation, true population mean for cholesterol is 175 plus or minus 2 times 5, 10. It's between 165 and 185. Let me think about this. Yes, I'm sorry. Go ahead.
Sorry, but you're saying that this is closer to the French mean.
Well, hang on a second. The French mean, which is the population mean, they know. We don't have to do any calculations there. The population mean for France is 160. In the United States, we just know the sample. So we know the sample mean is 175 for the United States. We're 95% sure that the true population mean for Americans, which we don't know, is between what and what? is between 165 and 175. 185. 165 and 185. And the French were 160. Well, the French are outside of that confidence interval. Think about that for a second. That means we're 95% sure that Americans have higher cholesterol than Frenchmen do. Without knowing the confidence interval, I wouldn't have been able to say that, right? I would have said, oh, they're 170. Americans are 175. Frenchmen in a sample, Frenchmen are 160. But I don't know the variability of the Americans. Maybe that 175 is just by chance that those particular 100 people were higher, right? But now I can quantify my level of certainty, and I can say with at least 95% certainty the two populations are different.
So if the French, whatever the weight is falling to the confident interval, means the
We can't be more than 95% certain anymore, right? In other words, if the French cholesterol was a 167, right? Right, it would be inside of our. It's possible that the American is the same.
right.
So we couldn't say with 95% confidence that the two populations are different, right? So, and if we wanted to be 99% confident, we'd have to use a wider range. French would have to be outside of that wider range. A lot of times now, think about this now. Now we can apply it to a study where we look at Frenchmen and we look at Americans and we do a sample of both populations. Now we have a confidence interval for Frenchmen. Let's say that that's 150 to 170. And we do a confidence interval for Americans, and that's 160 to 180. 150 to 170, 160 to 180. They overlap. So it's possible that they're both in that range where they overlap. I can't say that with 95% certainty they're different. But if they don't overlap, I got a pretty good idea that they're going to be different with a certain level of certainty. That's kind of the way that we're going to use this. We don't normally, instead of using this idea of non-overlapping confidence intervals, which sounds like a pretty good way to do it, statisticians don't do that. They do something slightly different, which is called hypothesis testing. That's the next thing we're going to learn about. And we're going to learn about, alpha error and beta error and all sorts of other interesting stuff. But it's really the same thing that we're doing now, except kind of repackaged. Okay, so now I got a homework assignment for you, and I just want to start on it so you can, give you a head start on it. Okay, and if you open it, it's on Blackboard. I changed it a little bit because I dropped out some stuff that we really didn't cover today. Okay, and it's a special assignment for Halloween. Okay, so we're going to go over the first one. Okay. Confidence interval of a sample mean. Population sigma is known. Zombies' primary food source is brains and spinal cords. Diet high in protein and low in carbohydrates. Form of a low-carb diet. Serum cholesterol levels are measured in 25 randomly selected adult zombies. Okay, the mean sample is found to be 151.4. The population standard deviation, sigma, for zombies is assumed to be the same thing as for living humans, 38 milligrams per deciliter. Okay, and there's a zombie food pyramid. They tend to eat a lot of brains and somewhat less hearts and lungs and stomachs and bones. And gristle they gnaw sparingly. It's not good for them, so they shouldn't have that much bones. Just like American food, human food pyramid. Calculate the standard error for zombie cholesterol. Okay, let's take a look at that. Let's calculate that standard error. Okay, let's get some space here, and let me get my stuff here. Okay. So my mean, X bar, is 151.1. 151.4. My sample size is 25. Now we know sigma in this case, right? We know sigma, and sigma was 38. Okay, so let's calculate our standard error. Our standard error is going to be equal to our sigma, population standard deviation, divided by the square root of 25, which is going to be 7.6. Okay, so the first question is calculate standard error for zombie cholesterol. We did that, 7.6. Calculate the 95% and 99% confidence interval for the mean cholesterol level for all zombies. Okay, so that's going to be equal to, it's going to be equal to X bar, right, minus, and in this case, since we know the population standard deviation, even though it's a small sample, what am I going to use here? What number? 1.96, I'm going to use Z because we know the population standard deviation. If we didn't know the population standard deviation, I would have used the T-score instead. 1.96 times 7.6. Okay, and equals 154.4 plus 1.96 times standard error. And that's our 95% confidence interval. Okay, now let's do the same thing for 99% confidence interval. It's going to be equal to our mean minus, what is it going to be this time? What is it going to be? 99% confidence interval. What are we going to use for Z? 2.58 times our standard error. And it's going to be equal to 151.4 plus 2.58 times our standard error. Okay, so that's good. This is our 95% and our 99% confidence interval. Okay. Okay, now this time we're going to repeat this, except this time that 38 is going to be the sample standard deviation, not the population standard deviation. So, well, sigma is calculated, instead of sigma, it's going to be S. Sigma, standard error is calculated exactly the same way, right? No change there because I didn't change the sample size. I only changed the fact that I didn't know it was population standard deviation. Still, it's a small sample, right? So I need to use T instead. So let's use T instead for a sample size of. I'm going to change that. I'm going to make it because we just used that number. I'm going to make it a sample size of 20. Okay, you can do it in the homework. You can use the real number. Notice the standard error corrected because it took the square root of, 20 instead, divided it by the square root of 20. So it came out to be about 8.5. Okay, so a 95% confidence interval is going to be equal to the mean minus, now what am I going to use for a T-score for a sample size of 20? Well, I got to go to the T-table, right? And for a 95% confidence interval, what's my degrees of freedom? 19, and that's going to be 2.093. Good, excellent. It's equal to 2.093 times my standard error equals, and now equals, let's see, 151.4 plus, I forgot it already, 2.093. I'm shot. You get to a certain age, you're lucky you can find your way home. Don't laugh, it's not funny. Equals, you really get a little, it really is harder to remember stuff, let me tell you. Too much stuff stacked up in there. 151.4 minus, now 99% confidence interval. I go back to the same table, except the column I'm using is the second one from the end for 99% confidence interval. And my degrees of freedom is still 19, so it's going to be 2.861. 2.861 times my standard error and equals 151.4 plus 2.861. I remembered it that time. What a miracle. Okay, and there's my confidence interval. So my confidence interval is wider when I have to use T because it's making up for my level of uncertainty because I don't know the population standard deviation. And this is real, there's as I summarized before, there's a lot of different situations that you could be in. And based on the situation, the information you have to make a decision. Am I going to use a T-score? Am I going to use a Z-score? But mechanically, it's the same calculation. over and over again. Which z-score, which t-score is based on a confidence interval. Yes.
So it's more of a practical application question.
Sure.
So if we were going back to that French and US
Sure.
example.
Yes.
So basically, if the French cholesterol had been, if we were 95% sure that the French cholesterol was outside of our range,
Yes.
then, and say like our diets were the same,
You'd have to look
then
for
that
some
would
other
be-
reason. All you're finding out, all you're measuring is a difference.
Right,
But then there's a whole other, range of things you have to do to figure out why is there a difference because of genetic difference? Is it is it exercise? Is
right,
it,
so say that like the diets were the same.
yes?
Right. Then you would basically be saying um that like we know that our cholesterols are different
You want it?
95% of the time because
No, it's not different 95% of the time. We're 95% certain that Americans have the average American has a different cholesterol than the average Frenchman.
yeah.
Right? Now, there could be a lot of Frenchmen that have higher cholesterols than Americans. And there could be a lot of Americans that have lower cholesterol than Frenchmen as individuals. But the average for Americans and Frenchmen is different. And what we're saying is we're 95% sure that that Frenchmen are different than Americans because we're 95% sure that Americans are within this range. And since the true average for Frenchmen is outside of that range, we're 95% sure that the true mean for Americans is different than the true mean for Frenchmen, because the true mean is 95% sure of it's between these two numbers. So if you're comparing it to a number outside that range, you're 95% sure it's different than that number, right? So that's really all you know. You don't know why. You don't know how much different. You don't literally don't know how much different, because remember, if our 95% confidence interval is 165 to 185, then the true population mean for Americans could be anywhere within that 165 to 185. You just know it's different than the 160 for Frenchmen, right? With 95% confidence. And if you want to know with more confidence, use a wider confidence interval. And it's entirely possible that the numbers could be such that 95% confidence interval, the French mean falls outside the confidence interval. And then when you go to 99 and it's wider, now all of a sudden it falls inside. So you can't say you're 99% confident they're different. Yeah, that could happen, or it could be still outside the range. Okay, but we're gonna get more into that when we get into hypothesis testing. Now, really, statisticians don't really use confidence interval in that way to test, whether or not two populations are different. They use the same principles, right? They apply the same principles, the t-score, and so on and so forth. They set up a hypothesis. They do a hypothesis test. They set up a null hypothesis, where a null hypothesis might be null meaning no difference. A null hypothesis might be there's no difference between mean cholesterol for Americans and for Frenchmen, right? And then they try and disprove that. And by disproving that, they then propose an alternative hypothesis literally called the alternative hypothesis. So you want to prove that the two numbers are different, two means are different, in order to reject that null hypothesis and accept your alternative hypothesis that they're different. Null hypothesis is you assume to start that they're the same, and then you use your evidence to prove that they're different. Okay, that's more the way that uses a function called a t-test. You actually calculate a t-score for the difference between the two of them. How many standard deviations apart are they? If you knew the population sigmas, you might call it a z-score. You might use a z-score. But since you never know that really, it's called a t-score. But you actually figure out how far apart are they really in terms of standard deviations. So that gives you what level of certainty you can say that they're different. So statisticians tend to use that structure of null and alternative hypothesis testing, rather than use the confidence interval to test whether two populations are different. However, that confidence interval is a really good tool because it really gives you a handle on how accurately you know a population standard deviation. Okay, so you have some other problems there that also involve some creatures of the night for Halloween, and I think there's 5 altogether. I will, I'll post a place where you can post the answers and stuff like that, so you can check to see if you got them right or wrong. There's only one other thing I wanted to mention, is that when you have a proportion, right? Things are a little bit different when you have a proportion, aren't they? First, the way that you use the way you calculate the standard error when you have a proportion. If I said to you that 70% of Americans we took a sample of size 100, right? I put a formula up on behind me. We took a sample of size 100, and I found that 70% of Americans have high cholesterol. PCAP, that's their sample of 100. We call that the true proportion, whatever it is, we don't know because you have to test every American. The true proportion is P. The average, like X bar, is PCAP, right? That's for our sample. We say PCAP for our sample is equal to 0.70, okay? And the sample size is 100, okay? N is 100. Okay, so now I need a standard error for that proportion. In other words, what's my 95% confidence interval for that proportion, 70%? Am I 95% sure that the population of Americans is 60 to 80%? 65 to 75%? What's my 90? Just like with our mean, we can have a confidence interval for our true population proportion. So in order to do that, we have to do the same thing, except we use the proportion PCAP instead of X bar. And for the standard error, we use this formula behind me. The standard error is equal to the square root of P times 1 minus P over N. Okay, well, our estimate of P is our sample. So it's 0.7 times 0.3 over the sample size 100, and you take the square root. That's your standard error. In the case of that, it's 0.7 times 0.3 is 0.21, right? 0.21 over 100 is 0.0021. Find the square root of 0.0021. Square root of 0.0021. 0.0021 square root is 0.045, about 4.5%, right? So our 95% confidence interval for the true proportion is going to be 0.70 p-cap plus or minus, what am I going to use, 1.96, or am I going to use a t-score? What's the sample size? Sample size is 100. It's a big sample. So do I use T or Z? Since I use Z, right? Because it's a big sample, right? So now, I use 1 point, so it's p-cap plus or minus 1.96 times my standard error, which was 0.045. In other words, basically, a plus or minus 9%. So it'd be 61% if you actually calculate it out. Well, you may say to yourself, well, how do you use T in that situation, Tony? You don't. You never do. One of the rules when you use proportion is you have to have a sample size of 30 or bigger, or you don't do it, right? So you don't use T, you don't bother with T when you work with proportions because you're always going to work with a sample size that exceeds what you would use to avoid using T if you could. Now, there's another rule. Now, remember I told you that sample size of 30, right? Well, if I think about that, if 70% of Americans have high cholesterol and I took a sample size of 30, that would mean 21 have high cholesterol and 9 don't, right? 70% and 30%. 21 would, 9 don't. Not good enough. Not only do you have to have a minimum sample size of 30, but you also have to have at least 15 individuals in each of the two groups. So that's too small a sample size.
Would you give a question like that and leave space for like this value cannot be computed?
No, I don't think I would trip you up. On a test, I wouldn't trip you up like that. Okay. So we would give you an example that would make sense. So if that in that case, it would have to be a minimum sample size would have to be like 50 because then 70% of 50 is 35, and that would leave 15 in the other group. Okay. So and that's how you would do the problem that follows the one that we just did. Okay. So we're at about 750, right? Class ends at 750.
Would that change your standard
What's that?
error calculation?
No, our standard area, well, no, wouldn't, right? Because our,
You still
yes,
do
the sample
proportional
size,
calculation?
the sample size would change it,
Would change.
right? Because then it would be 0.7 times 0.3 over 50 instead of over 100 or whatever, right? Remember, the standard error is always based on the sample size to some degree.
Yeah, but you wouldn't be calculating for just the 70% of the
No,
sample size,
no,
right?
you're still P times 1 minus P,
Yeah.
right? People that are and people that aren't. Okay, both sides of the